Hello, AP Calculus. This is section 3.2, basic differentiation rules and rates of change. I think you're gonna like this one a little bit better. Now, the very first item I have is our definition, okay? It's a definition of what we call a power rule. And the idea is this, and it follows my original function, which is up here, this f of x equals x to the m power. And if I want to know the derivative without having to do my limit rule, okay, then the rule suggests this, that you take your power and you move it to the front, okay, and then you take your power, whatever value that is, and subtract 1 to it. Okay, and that's what you have right here. I am taking the derivative with respect to x for this x to the n term, and the rule is that you move the n out to the front, and then you multiply it by the x to the n minus 1 term, okay? All right, now there is a proof for this, and here's what I'm gonna do. I'm gonna skip it for now, and then at the very end of my lesson, I'm gonna go back to it, okay, and then explain it again, all right? So if you wanna check that out because you're curious to know why this works mathematically, then great, I can show it to you. If you're not interested, then that's okay, because I'm not gonna ever test that on you, okay? All right, so let's use this rule to answer some of these simple questions. It says rewrite the function with the exponent in the numerator, then find the derivative, okay? So the nice thing is that this first item already has a power in the numerator. This is really x to the 6 over 1. And so if I take the derivative of this, it's quite simple. I'm gonna move the 6 out front, and the x is the term that will repeat, and then I have to subtract 1 from this. And 6 minus 1 is 5, and you can stop right there. Had you inputted this function, x to the 6, to our limit formula, delta x goes to 0, and you would have done, geez, x plus delta x to the 6th power minus x to the 6 all over delta x, you would have ended up with this same result. Okay, now, if for fun you're having a math party or something and you want to do this on a Saturday night, a long ways, knock yourself out. Okay. All right, now the next one, you're like, where's my power? It's there. This is really x to the, well, remember the number in the inside, if there is no power, is a 1. And a root bar, if you don't see a number there, then we assume it's a 2. Okay, so we must know that the square root is the same as x to the 1/2 power. All right, now, when I take the derivative here, okay, I'm going to move the 1/2 out front, because that is the number, that is my power, move that out to the front, times x, and then I have to subtract 1 from this, okay? So if you think about it, 1/2 minus 1, you can use a calculator if you want, but that does give me -1/2, which I bet you already know. All right, now what does that mean? Well, if I want to make this look a little bit nicer, I have a 2 in my denominator, and if I want this power, which is a -1/2, to be a positive, then I'm going to move that to my denominator. Okay, and if you want to finish this, you can write it like that. Some will say, do I have to? And if it's a free response question on an AP exam, you can really stop right there. However, they'll oftentimes ask you to put in a number for this x, and you'll have to work it out, okay? So there you go. In time, you'll get in the habit of just knowing that the derivative of the square root of x is 1/2 square root of x, where the square root of x is in the denominator, and you won't have to show all this stuff. It's just kind of a natural, instinctive thing. Again, the square root of x, the derivative of that is just 1/2 with the square root of x on the bottom, okay? All right, now, this last one has to follow the first rule that is discussed. It says rewrite the function with an exponent in the numerator, okay? Here's what you don't want to do. Do not say that y prime is 1/4x to the 3rd. If your power is in the denominator, it's not valid. Okay, this only works when your power is in the numerator. Okay, so what I'm going to do is rewrite this in a similar form, and I'm going to put this x to the fourth on top. Okay, and you're allowed to do that. Okay, you can move powers from denominators and numerators and vice versa, provided that you change the sign to its opposite. Okay, so you're going to change the sign of the power to its opposite. Okay, and now we'll take the derivative. Okay, so your -4 will drop to the bottom, and we'll multiply it by x, and then we have to take -4 and subtract 1 to that. Okay, and -4 minus 1 is -5. Okay, and again, this x is -5. I would prefer it to be positive, so I'm going to make it positive by putting it in my denominator. Okay, all right, so this is the most basic, most fundamental form of a derivative that's easy to do in this most simplified fashion. However, most important part as you start these is to make sure that your exponent is in the numerator. All right, let's move on. Next type of question is very similar to previous ones we've had in other days. Find the equation of the tangent line to the graph of f of x equals x to the third at x equals 2. Now, I'm just going to draw a little rough graph of this here. This is a inverse Travolta, something like that. And at 2, there's going to be some equation of a tangent line. And I almost don't want to draw it because it looks like it's too hard to draw. Good enough, all right? And so I need the equation of that line, whatever it may be. And so when I think about the equation of the line, I'm going to write, again, my point-slope form. Okay. And so what's nice is I already have one of my 3 values. This is 2, and that's what x is, and I'm going to put that in for this first position. All right, now, sometimes this is the hard part because it's really the non-calculus part. I should be able to know what y1 is too. And sometimes people look at that and say, I don't see a y1 written. And the way we find that is just by plugging 2 in for this f of x. Meaning you're going to plug it into the x where the f of x is. So basically I have f of 2 is equal to 2 cubed, and that is 8. So that goes here. All right, now my last step is I have to take the derivative of this, okay? Remember that a slope is your rate of change, which is a derivative. So what I'm going to do is I'm going to take the derivative of x using our power rule, okay, which means the 3 will come out front and x will be by its side. And then you're going to subtract 1 unit from the 3, and that will give you a 2. All right, now common mistake. Sometimes students like to take this and put this in for the m. And not quite, okay? We usually have slopes that are represented through numbers, okay? In fact, we want the slope not for any number, but for a specific one, and that's when x equals 2. All right, so we're going to say f prime of 2 is equal to 2 cubed. Sorry, not 2 cubed. It's equal to the derivative, which is 3 times 2 squared. All right, so 3 times 2 squared. Make sure you do your order of operations correctly, perform those correctly. 2 squared is 4. And then when you multiply 3 by 4, you'll get 12. What do I do next? You do nothing next. You leave that as it is because the only thing you do is get marked off. You cannot enhance your point total by simplifying for y. Okay, so we'll just leave it as is and we will move on. All right, now this rule is basically the same as the others. The only difference is that you have a number that's out front. Okay, a number out front meaning a coefficient. And the rules don't change any, okay? If I'm taking the derivative here with respect to this x, this n will come down, as you see happens right here, and then you subtract 1 to the power. All right, so if I'm taking the derivative of 4x squared, okay, I'll say y prime is equal to, the 4 will stay, and then you just move the 2 down, and then it becomes x to the 2 minus 1 is 1. All right, and then we'll multiply that 4 times 2 together. Sometimes students will say, do I have to show all these steps? And the answer is no. All right, I know that you can take this 2 and just multiply it by the 4 and get 8 and subtract 1 in your head. That's no big deal. Okay, so no, you do not have to show work. Be careful on this one. It's a fraction, but it's much more easily done if you move the 1/3 out in the front. Okay, now let's think about this. All right, I didn't do any calculus yet. I just rewrote it in a different way. This is a third times x. It's the same thing as the fraction x over 3. And I have a power of 1 there. Okay, so by rule, what I'm going to do is I'm going to move this 1 to the front and multiply it by the third. And so a third times 1 is just 1/3. And it becomes x to the 1 minus 1, which is 0. Okay, now remember, a power of 0 is unique. Okay, anytime you have a power of 0, what that suggests is that this value is 1. Okay. So be careful not to make this power of 0 also go to the third. It only goes to the base that you're taking that power to. All right, part C. Again, this doesn't look good because I have an x value in my denominator, and I don't want that there. So I'm going to move it to the numerator and put that to the -1 power. And from here, I can now do my calculus. Okay. Let's move this -1 to the front and multiply it by the 3. And let's now subtract 1. Now be careful. I'm going to write this off to the left here. -1 minus 1 is not 0. A lot of times students will accidentally do that. That's actually -2. All right, so this will give me -3 over x squared. All right, I have one more just like this. And again, you'll notice 2 ugly things about it, maybe even 3. One, it's negative, and that just gives me a negative feeling to start with. Okay. Second is you have an x in the denominator, okay, which offers us a little bit more work. And the third thing is that your x doesn't have a power. It has a radical sign with a 3 with it. Okay, so we're gonna have to clean this up a little bit before we even consider doing the calculus part of it. Let's first write this as an exponent. Okay, so remember the item in the inside, this is x to the first power, is going in the numerator, and then the cube part is going to go in your denominator. Okay, and that's not really the cube, it's the cubic. All right, so that's our first step. And again, this is a negative. And then the second part is I want to move my exponent to the numerator. All right, so I can do that. I can move that up to the numerator with the x, but I must change the power. Okay, and then you have a 2 on the bottom. All right, and then my last step is to actually do the calculus piece. All right, off to the right here, I'm going to write y prime. Okay, again, notice the 2 didn't come up, and that's because it didn't have the power of 1/3 with it. Okay, if you had parentheses, then the whole thing would come up, but that wasn't the case. All right, so I'm going to drop this down. I'm going to multiply -1/3 times, really this is -1/2, so it's -1/3 times -1/2, okay, x, and then you're going to have to subtract 1 from -1/3, -1/3, excuse me. Okay, so -1/3 minus 1 is -4/3. Okay, and then we can make this look a little nicer. A third times a half is really a 6, and it is positive because a negative times a negative is a positive. And this x to the negative 4/3 is really x to the positive 4/3 when you put it in your denominator. All right, questions? All right, let us move on then. Okay, now here's what we got. These are just basic rules, and I'll show you how this works in just a moment. So it's the derivative of trig functions, and you're not going to learn them all today. You're just going to learn 2 of them. You're going to learn the sine of x and the cosine of x. And if you've taken any type of calculus in the past, you know the derivative of sine is cosine, and cosine x, and the derivative of cosine x is negative sine x. Okay, now, a lot of times people will say, why? Let me see if I can show you. I do not have a straight edge, so I will have to use my cell phone, which is kind of straight. Let's see. Okay, now I'm going to do my best to draw a sine curve. Okay, and that goes to 2 pi. Okay, now here's what's going to happen. This is sine x. This is my f of x. And what I'm going to do is I'm going to find points of tangency at certain locations. Okay, so for example, what I can tell you is that the sine of 0, the tangent line here is going to have a slope of 1. Okay, so this is a slope of 1. At pi over 2, your tangent line would have a slope of 0. At pi, okay, if you were to draw the slope of a tangent line, something like that, okay, it would actually be a -1. And if you were to do this at 3 pi over 2, it would be at 0. And then if you did 2 pi again, you would get the same thing you had over here, m equals 1. And I know that's not drawn to scale. I wish that was a little bit more, not increasing so quickly, but that's just how it is. And here's the idea. This is what I'm going to do. I'm going to, Rothri. I'm start over.